Hi, hello, welcome to Jadav's Academy. In this class, I am going to discuss about a solution for previous questions which are asked in TS E-Cet 2020 in the subject reinforced cement concrete. So let us start our discussion. The first question which is asked in TS E-Cet 2020 in RCC subject is, as per IS 456 2000, the partial factor of safety for concrete is. So if you refer your code book, that is IS 456 2000, in class number 36.4.2.1, so there is a condition that the partial factor of safety, that is gamma m. Gamma means a partial factor. M refers to the for materials. So gamma m should be taken as 1.5 for concrete and 1.15 for steel. So we have in reinforced cement concrete, we are using two types of material. One is concrete. For concrete, the partial factor of safety is 1.5, and for steel it is 1.15. So let me check the answer for this question, options for this question. See, option A is 1, option B is 1.5, option C is 1.15, and option D is 1.75. Right. According to this IS 456 2000, the partial factor of safety in concrete will use is 1.5. So the option B is correct for this question. So let us discuss one more question. Here, in an under reinforced concrete beam, these are the options. Actual depth of neutral axis is less than the critical depth of neutral axis. The moment of resistance is less than that of the balanced section, and the actual depth of neutral axis is less than the critical depth of neutral axis, and the moment of resistance is less than that of the balanced section. And the option D is the actual depth of neutral axis is more than critical depth of the neutral axis. So to arrive the answer for this question, let me explain what are the characteristics of under reinforced section is. Say this is a beam section, right? This is a beam, and for this beam it is a neutral axis, okay? And this tension zone of a beam will provide a steel reinforcement, and if I draw the strain distribution diagram for this, it will be linear like this. It will be linear like this. So this is a compression zone. So we have a compressive strain here, and it is a tension zone. So we have a tensile strain here, right? A section said to be a under reinforced section. In this, our steel will reach its maximum permissible strain first, then our concrete reaches. That means first steel will fail, right? After failing the steel, then concrete will fail. Say this is our strain distribution diagram in under reinforced section. See here, our steel is completely failed here. It reaches maximum strain here. At this time, still our concrete is under straining, right? So this is the critical depth, I can say, the depth of neutral axis corresponding to the maximum depth, that is XU max, right? This is XU max, or the depth of neutral axis corresponding to the balanced section, and this is what, because of the steel strains first, or the steel reaches its permissible value first before concrete reaches its permissible value. So this is what actual depth of neutral axis, right? This is a definition, actual definition of under reinforced section. So in these conditions, I will draw 2 or 3 points regarding under reinforced section. Here, a section said to be an under reinforced section, your actual depth of neutral axis XU must be critical depth of neutral axis or a maximum depth of neutral axis XU max, right? This is one more point. Okay. Then second point is the moment of resistance in under reinforced section. The moment of resistance in under reinforced section, that is ORS, is less than moment of resistance that of in balanced section, the balanced section, right? Right. So one more point I can make here. The failure occurs is in this type of section is a ductile failure, as our steel is failing first. Our steel as a ductile material. What is that? A ductile material. So ductility means what? So before failure of steel, it will become small thin wire. Small thin wire. That is called a ductility of the steel. The failure occurs in under reinforced section is ductile failure. Okay, na? So let us see based on three important points which option is correct for this question. What is the first option? Actual depth of neutral axis is less than the critical depth of neutral axis. Okay, it is accepted point. Let's see any other options have better than this option. The moment of resistance is less than that of the balance section. This is also correct, right? And in third option, the actual depth of neutral axis is less than the critical depth of neutral axis. So the first point is valid, and the moment of resistance is less than that of the balanced section. Second point also valid, right? Then fourth, see the fourth option, actual depth of neutral axis is more than critical depth of neutral axis. So it is not, it is for this case we will get a over reinforced section. So after observing all these four options, the option C is the correct option for this question, right? These two for this question, these 2 points are related to this under reinforced section. Okay, so option C is the correct answer for this question. Let me discuss one more question here. The effective width of the flange for a T-beam may be taken as where dF is the depth of the flange and BW is the width of the flange and L0 is the distance between point of zero moments. We can call it as a effective length. Okay, so let me draw here the plan of beam and slab system, that is a roof slab. So nowadays we are casting a beam and slab are monolithically, right? That means your beams and slabs are casted at the same time under the same formwork. So the plan of that will be look like this. So these are the beams which I am drawing now. Okay, these are the beams. See, this resembles like your alphabet T, so we can call a T beam. We can call it as a T beam. See here, this portion from here to here and this portion is resemble like a alphabet called T, so we can call it as a T beam. And the end beams are resembles like a L, so you can call it as a L beams. Now our discussion is about only T beams, so let me discuss about only about the T beams, right? So this shaded portion is T beam. Then this will be the actual width of the beam. But in question, it was asked that what will be the effective width of the beam? Effective width of this T beam. So what do you mean by effective width? The width on which a T beam can effectively resist the forces. That width of the beam is called effective width of the beam. Say, I will draw separately here the T beam is. Right? This is a T beam. Here I am drawing separately. Okay. So over this T beam, if you apply a load over here, definitely it will bends like this. Right? If you apply a load over here, here also it will bend like this. And similar with this case, if you apply load here, it will bend like this. If you apply load here also, it will bend downward. But between this portion, if you apply a load, it will not bend, it can effectively resist the load which are coming onto this beam. So this width is called effective width of T beam, that is B suffix F. BF is the effective width of the beam, right? This BF is effective width of the beam. BF is always less than actual width of the T beam. If now you can compare. So this is the actual width of the beam and this is effective width of the beam. If you observe, our BF is less than B. The always the effective width of the T beam is less than the actual width of the beam. Right. The formula for calculating this effective width of a beam or effective width of flange of a beam as per IS 456 2000, the formula given is this one. If you refer a code book IS 456 2000, then you can, you know, the calculation of effective flange width of a T beam is L naught by 6 plus BW plus 6 into DF. L naught is the effective length of the beam, that is the distance between the point of zero moments, and BW is the width of the web. So this is the web portion of a beam. This is width of the web, and DF is the depth of the flange. So this is the flange, right? This is the flange. The depth of this flange is what you can call DF. So for calculating effective width of the flange of a T beam, the formula what we are using is BF is equal to L naught by 6 plus BW plus 6 into DF. So option B is the correct answer for this question. So let us discuss one more question. Here, according to the IS 456 2000, the HYSD bar, HYSD means high yield strength deformer bars, the reinforcement in either direction of a slab shall not be less than. So let us see codal provision for this. What is the codal provision we have for this? In code IS 456 2000, in the class number 26.5.21, they have given minimum reinforcement required. What are they given here? The mild steel reinforcement in either direction in the slab shall not be less than 0.15% of total gross cross-sectional area. So what do you mean by this? What do you mean by mild steel? The mild steel nothing but a Fe250 grade. So if you use Fe250 grade reinforcement in the slab in either direction, then the minimum percentage of reinforcement should be provided is 0.15% of gross cross sectional area. 0.15 percentage of gross cross sectional area. Now if we read out the second point, however, this value can be reduced to 0.12% when high strength deformed bars or the welded wires fabrics are used. So what do you mean by these high strength deformed bars? That is HYSD bars. If you are using reinforcing material or reinforcing steel, the grade of steel is Fe 415, that is 415 called HYSD bar, then the minimum percentage of reinforcement used is 0.12% of gross cross-sectional area. So what is asked in our question? As according to the IS 456 2000, if you are using HYSD bar in the either direction of slab, the what is the percentage of steel should not be less than, that is, here if you see the option A, 0.1%, 0.12%, 0.15% and 0.20%. So according to this class, that is 26.5.2.1 of IS 456 2000, it is 0.12% of gross cross sectional area when we are using reinforcement as a HYSD bars. So option B is the correct answer for this question. Option B is the correct answer for this question, right? So let us discuss one more question here. Here again they have given some codal provision. What is the question? The final deflection. The final deflection in a beam due to all loads including effect of temperature, creep and shrinkage should not normally exceeds, right? For control of deflection as per IS 456 2000, in class number 23.2, there are two conditions are given for deflection, right? And these two are two different conditions, and in two conditions they have taken different parameters. So let us see the first condition. The final deflection due to all loads, the effect of temperature, creep and sinkage, and measured from the as cast level of the support floor, roofs and all horizontal members should not normally exceed span by 250. What is that? Span by 250. It should not less than or should not exceed, should not be greater than, we have to write should not be greater than span by 250, right? If you observe the second condition, in that condition they are given only the deflection including the effect of temperature, creep and sinkage occurs after erection of partitions and appliances of finishes should not normally exceed span by 350. How much it is? Span by 350 or 20 mm, whichever is less. So what was asked in our question? That is the final deflection and beam due to all loads, all external loads, including temperature, the effects of temperature, creep and shrinkage. So this is related to our first condition. The final deflection due to all loads, including effects of temperature, creep and shrinkage. The deflection should not normally exceed, that is span by 250. Span by 250. So we will see the options here. Option A, span by 500. Option B, span by 350. Option C, span by 250. And option D is 20 mm. Here they are considering all loads including other effects like temperature, creep and sinkage. For this case, code has given the deflection should not exceed span by 250. So for this question, option C is the correct answer. So let us discuss one more question. It is a simple question here. The maximum area of tension reinforcement in the beam shall not exceed, where D is the effective depth and B is the overall depth of the beam. So let me draw a cross section of beam here, right? And this is here we have provided reinforcement. So how to calculate the overall, that is cross sectional area? The cross sectional area of this beam is, this is the overall depth, capital D, and this is width of the beam, small b, right? So this is small b. The gross cross sectional area is overall depth multiplied by width of the beam, right? So the maximum area of tension reinforcement in beam shall not exceed. So as per IS 456 2000 in class number 26.5.1.1 about the tension reinforcement, in the point B they have given that about maximum reinforcement. The maximum area of tension reinforcement shall not exceed 0.04 times B into D. What is the B into D here? It is a gross cross sectional area. So it should not be greater than 0.04 times gross cross sectional area, that is B multiplied by capital D. It is also called, that is simple, 4% of B into D. Other way we can call it as how much? 4% of gross cross sectional area, that is 4% of B into D. So let us take the option for this question. Option A, 0.04 times of BD. Option B, 0, here small b and small d. You have to observe this condition also. Small b is the width of the beam and small d is the effective depth, right? Those things you have to observe here. And b is equal option B is 0.04 small b capital D. So this will give the gross cross sectional area. And option C is 0.06 times small b and small d, and option D is 0.06 times small b and capital D. So according to this class, the maximum area of tension reinforcement should be provided in beam should not be less than, that is 0.04 times gross cross sectional area, that is capital D into B. So option B is correct for this question. So let us discuss one more question here. Again, it is based on the IS 456 2000 clauses. According to IS 456 2000, the maximum compressive strain in concrete under axial compression is So this question was many of the students may have done mistake because we have the maximum strain in flexure and the maximum compressive strain in compression also, right? If you see the options here, those two options are present in or given four options, but you have to read the question carefully whether it is asked maximum compressive strain in flexure or the maximum compressive strain in compression, that we have to differentiate. So according to the IS 456 2000, the maximum compressive strain in concrete under axial compression, the given is under axial compression, right? So under axial compression, according to the clause number 39.1, that is assumption made for design of columns. So here we have two subpoints, that is A and B. If you observe the point A, the maximum compressive strain in concrete in axial compressive strain taken as 0.002, right? So if you see the options here, option A is 0.0025, option B is 0.0035, and option C is 0.0030, and option D is 0.0020. So according to this assumption, the condition A is satisfies here, that is the maximum compressive strain in concrete under axial compression is 0.002. So option D is correct. So to confuse you, one more option also given, that is option B, that is 0.0035. It is a maximum compressive strain in flexure condition. It is in flexure condition. So don't confuse with these two options, flexure condition. It is in compression, maximum compressive strain in compression. So it is related to the columns, as a column is a compression member, and this strain is related to the beams. Okay, na? Right. So let us discuss one more question. Here, according to the IS 456 2000, the compression member is said to be a called as a long column when the ratio of effective length to the least lateral dimension is exceeds 9. Option A is exceed 9, option B is exceeds 15, and option C is exceeds 12, and option D is exceeds 3. So I will explain you the story of compression members here. When we call a long column, when we call a short column, when we do, how we classify the pedestals and the columns like this. So if you take the ratio between L effective to the lateral dimension, that lateral dimension may B or D, B or least lateral dimension may be width of the column or depth of the column also. Among these two, any one of the dimension may be the least lateral dimension. So let us draw a column here, right? So this is a column or a compression member. Before I talk about column, I will call it as a compression member, right? This is a compression member, okay, right here. And if this is a B and this is a D. Here I am calling as B, width of the column and depth of the column, both are a lateral dimension for the column. So this is height of the column is a longitudinal dimension. The dimensions which are perpendicular to the longitudinal dimension are called lateral dimensions. So this is a height and this will be the perpendicular to the height. So these two dimensions are perpendicular to this height. So B and D. Here I have a plan of that column, say. So this is a B and this is D. These two are the lateral dimensions. So sometime B may be greater than D or D may be greater than B. So we don't know which dimension is least. So that's why I written here effective length of the column by least lateral dimension among this B and D. one may be the least lateral dimension. Suppose L by E, effective length of the column by least lateral dimension is less than 3, then it categorized as a pedestal. What we can call it as a pedestal. Pedestal. Okay, right. If the same, that is L effective ratio between effective length of the column to the least lateral dimension is greater than 3, we can categorize it as a column. What is that? Column. What is that? Column. So among this column, there are two types of columns. One is a short column and long columns. Short columns and long columns. If the ratio between effective length of the column and the least lateral dimension, that is B or a D, is less than 12, then we can call it as a short column. If the ratio between effective length of the column to the least lateral dimension B or D, then we can call it as a long column. Right? Long column. If this ratio exceeds greater than 12, we can call it as a long column. The same thing in the appendix B of IS 456-2000 in 3.3, they are given the definition of long column here. That is the ratio of effective length of the column to the least lateral dimension must be above 12. Above 12. It should more than 12. So the option for this question is option C, that is exceed 12, then only we can call it as a long column. Right? So let us discuss one more question here. It is again related to the IS 456-2000 recommendations. So what is the recommended value of effective length as per IS 456-2000 for a compression member effectively held in position at both ends but not restrained against the rotation? So as per IS 456-2000 in table number 28, for effective calculation of effective length of a compression member, they have given some condition. So if you see this third condition, the column is effectively held in position at the both the ends but not restrained against the rotation. So this condition and the question what they are asked here, both are same. For this case, what is that? What is the recommended value of effective length? The recommended value of effective length for this is 1 into L. So if you see the options, option A is 0.65 L, option B is 0.80 L, and option C is 1 into L. So option D is 1.20 into L. So according to this condition, the option C is correct, that is 1 into L. So let's move on to the next question. So it is a very logical question here. Let me explain in detail about the design of footing and what is the critical section and what is the shear. So let us see what is the question is. In design of footings, the critical section for one-way shear check at a distance is at, right, when a footing is subjected to external load. Say I will draw the elevation or the section of a footing here. So this is a column. Generally footing will below the column, right? So this is the footing and this is the column here. When this column is subjected to when a column, the load applied over a column, that column will transfer the load onto the footing. In this time, your footing is subjected to these three important parameters. One is bending moment, another is one way shear, and second one is two-way shear. So while designing a footing, we need to take care of these three parameters, that is bending moment, one-way shear and two-way shear. Two-way shear. Right. What is the question asked? In the design of footing, the critical section for one-way shear check is at. First of all, what is the critical section? The critical section is a section where failure occurs in the footing. The critical section is a section where failure occurs in the footing. So the critical section due to bending moment in the footing is at the face of the column. Where it is? At the face of the column. At the face of the column. So this is a column. Here we have a critical section for bending moment. If it is one-way shear, the critical section occurs at d by 2 d distance, sorry no, d distance from face of the column. D distance from face of the column. D distance from the face of column. Face of the column. So where is the face of the column? So this is face of the column. And what is this D? This D is equal to effective depth of the footing. What is this D? That is effective depth of the footing. Right. So when we are checking the shear for one way, the critical section will occur at a D distance from the face of the column. So this XX will be the critical section. Yes. So if you check for two-way shear, the critical section occurs at d by 2 distance from the face of the column. The critical section occurs at d by 2 distance from the face of the column. Always this critical section, distance of critical section always should be taken along the longitudinal direction of the footing. Along the longitudinal direction of the footing. So our question is, where is the critical section for one-way shear check? That is, the option is D distance from the face of the column. So according to this question, option D is correct. That is a distance of small d from the face of the column. Here D is effective depth of the column. So why we are taking D for this? Means I will explain you here. When you apply a load over the footing, the load will disperse at an angle of 45 degrees. Load will disperse at an angle of 45 degrees. Now here with the horizontal, it is 45 degrees means here also a 45 degrees. We have the same angle here, right? And this will be the D. When it is 45 degrees, it will form a isosceles triangle. This triangle called what? Isosceles triangle. Means this side and this side both are same. When it is D, this also a D, right? Okay. And if you project this 2 point onto this, what is the distance here from the face of the column? It will be D. So like that, we will take a critical section for checking of one-way shear in the footings, that is D distance from the face of the column. So let us discuss one more question. It is a simple question. It is again codal provision. In design of footing, the minimum percentage of reinforced HYSD bars provided should be. It is a direct question from codal provision. As we are using HYSD bars, definitely will provide area of steel. The minimum percentage of steel is 0.12% of overall cross sectional area is the first option. The second option is 0.15% of overall cross section area, and third option is 0.2% of overall cross section area, and option D is 1% of overall cross sectional area. Right? According to the IS 456 2000, when you are using HYSD bars as a reinforcing material, the minimum percentage of steel to be provided is 0.12% of overall cross sectional area. Right? That is, for this question, option A is correct. Suppose in place of HYSD bar, if you have Fe250, that is a mild steel bar, then it would be how much? That is 0.15% of overall cross sectional area. So for this Fe250, if it is an Fe250, then the option B is correct for this question, that is 0.15% of overall cross sectional area. But for this question, we are using HYSD bar. So the minimum percentage of reinforcement to be provided is 0.12% of gross cross-sectional area. So let us see one more question here. So it is based on working stress method of design. So in working stress method of design, the modular ratio for M30 grade concrete is, so according to the IS 456 2000, the modular ratio can be calculated in a working stress method. The formula is 280 by 3 sigma C. What is that? 280 by 3 sigma CBC. So what do you mean by sigma CBC here? It's a bending compressive stress. What is that? Bending compressive stress. And this value depends upon grade of concrete. What is that? Or a characteristic compressive strength of a concrete, FCK. Right. And this FCK, this sigma CBC, generally one third of FCK. You will take one third of FCK. How much we can take? One third of FCK. So one third of a characteristic compressive strength of concrete. So to calculate the modular ratio for M30 concrete, first you have to calculate what is the sigma CBC is. A compressive stress in bending. How much? That is how much? Sigma CBC is equal to FCK by 3. So FCK by 3. Here FCK is the grade of concrete is M30. So the characteristic compressive strength of the concrete is 30 by 3. It is 10. 10 Newton for mm square. 10 Newton for mm square is the compressive stress in permissible compressive stress in bending. Permissible compressive stress in bending. Now substitute the sigma CBC value in formula of modular ratio, that is 280 by 3 into what is the sigma CBC? 10, right? So we'll get 280 by 280 by 30. 280 by 30. So this 0 cancel, and 1s are 3 9s are 27. Again we have 1. So 3 3s are, and again we have 1. 3 3s are. So the modular ratio for M30 grade of concrete is 9.33. So let us see the options. A is 10.98. It is not a right answer. Option B is 9.33. So it is the right answer. Okay. So this is option B is the correct answer for this question. So let us see one more question. It is again codal provision in working stress method. So what is the permissible tensile stress of a HYSD bar of Fe415 grade in working stress method of a design? So according to the IS 456 2000, if you observe the table number 22, they have given permissible stresses in steel reinforcement. Here we have type of stress in steel, and here we have the permissible stresses corresponding to the grade of steel. So in the question what they are given? Permissible tensile stress. So here we have to take what type of stress here? Tensile stress. Okay, and they are not mentioned in diameter whether greater than 20 mm or less than 20 mm. They have given which bar we have to calculate for HOSD bar of 415. So this is for mild steel, this is for medium tensile steel, and this is for HYSD bars of grade Fe415. So for Fe415, the permissible tensile stress of HYSD bar of Fe415 grade steel according to this IS 456 2000 table number 22, that would be how much? 230 Newton for mm square. So let us see the options here. A is 200 Newton for mm square. It is not a correct answer. And option B is 140 Newton for mm square. It's not a correct answer. And option C is 230 Newton for mm square. So it is the correct answer. So for this question, option C is correct. So thank you. That's all for today's lecture. So if you are watching my video for first time, please subscribe my channel and many more to come.